And we are almost live. We're live. There we go. Let's see if this works. Okay, so today what we want to talk about is exponential functions. And it is 2/03/2020, okay? So, exponential function, okay? So let's start, first of all, y equals ab to the x, okay? So there's two ways we want to write this, okay? ab to the x, where b is a base, okay? So b is the base, and a is the initial amount, or beginning, okay? And that's exponential form, but I like it this way better. And we're going to go instead y equals a times 1 plus or minus r to the x power, okay? These two will give you the exact same graph. Yep. It's a little confusing, but if you were here Friday and you did the Skittles, I want you to think about the pink Skittles real quickly. So I want you to think about the pink Skittles. If we did the pink Skittles, let me show you why these are the same. We always double, right? With pink Skittles, I think eventually you guys realize that you're just going to times by 2, and then you didn't have to do the pink anymore, right? And the reason it became 2 is because you started with 1, you added 1. Okay, so let me write both equations down. So if I look at the pink Skittles, I had a y equals, we started with 1. That was my initial amount, right? And we doubled every time. And you guys saw that. Yeah, Raleigh?
It's R.
R is the rate. And in fact,
I forgot what you said.
yeah, it's the rate. I'm going to write that down, okay? Okay. So what we did is we doubled every time, right? You guys agree with that? So the base is 2. These two are the same equation. I'll tell you why it's the same equation. We like this one specifically when we talk about percentages. Like for instance, if it increases by 6%, that's why I like the R. 6% would be 0.06, right? The Skittles are the same thing because it increased by 100%. So for the pink Skittles, we started with 1. We always added 1 for every pink. So what we did is we really added 100%. So the same formula works. Okay, so with the pink Skittles, we had a y equals a 1, parentheses 1 plus 1 to the x power. Okay?
So what about the equation for 31? Or if it went to 31, it would be 10 million something.
Right. We're going to start that. Yeah. Okay, so we normally would use this for any kind of percentage. Now I put plus or minus, and hopefully you know why I put the minus. What's minus going to do for us in this example? What's the minus mean in this example?
If it's exponential decay.
Exponential decay. Does that make sense? So I have the plus, it's growth, and I have the minus decay. Okay, good. So then, real quick, let's take a look at example 1. Oh, let's put this down. R is the rate, oftentimes as a percentage. Okay? So, example 1. So let's do a t-table real quickly. If I go x, y, and I want x to be 0, then 1, then 2, then 3, then 4, and then I actually want to go -1, -2, okay? All right? Biggest mistake kids make, but not you guys. No way. Biggest mistake kids make, but not you. No way. The biggest mistake kids make, but not you. Never, ever, ever, is they do this. Not my smart kids. They would never go 3 times 2. You'd never, because what's going to happen is as you put numbers in here, this is no longer 3 times 2. So for instance, if I put 0 in, anything with 0 power is 1. So it's really 3 times 1. See? Then I put in a 1 here, yeah, it's 3 times 2. But if I put a 2 in here, 2 times 2 is what? 4, so it's not 3 times 2, it's 3 times 4. It's not 3 times 2 because when you put a 3 in here, you get 3 times 3 times 3. I'm sorry, you get 2 times 2 times 2, which is 8. This is not. This is 3 times 8. This is not 3 times 2. You guys got it? So let's go ahead and do a t-table. So if I put in a 0, I get anything to 0 power is 1. 3 times 1 is 3, right? If I put in 1, 2 to the 1 power is 2. 2 times 3 is 6. Now that one is true, but not all the way. Put a 2 in here. 2 to the second power. 2 to the 2 power is 4. 4 times 3 is 12, right? If I put a 3 in here, I get 2 to the third power is 8. 2 to the third power is 8. 8 times 3 is 24. If I put a 4 in here, 4 to the fourth power is 16. 16 times 3 is 48. So do you see the pattern? What's going on here? It's doubling. And that makes sense because what's my rate? 2. I'm doubling. Yeah.
Would the next one be negative 6 or 6?
Great question. Let's do it. So I'm going to go 2 to the negative 1 power is 1/2. 3 times 1/2 is 1.5 or 1.5. Okay. 2 to the negative 2 power is 1/4 times 3 is 3/4. Okay, so I'll do that down here. I want you to see this. 3 to the negative 2 power is 3 times 1/2, which is 1.5. I want you to see that if you didn't get it.
3/4?
And then 2 to the negative 2 power is 3 times 1/4, because of negative exponents, which is 3/4 or 0.75. Okay, so if we graph this, these are my x values, right? And then I've got a value at 0 is 3. That's my initial amount. My initial amount is going to be on the y-axis. 1 and 6, 1, 2, 3, 4, 5, 6. 2 and 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3 and 24 is way off my graph. 4 and 48 is way off my graph, right? It's exponential. However, negative 1 and 1.5 is about there. Negative 2 and 3/4 is there. So here's what I know. Before I connect my dots, this is what I know. I'm going to draw my graph like this. I'm going to draw it in such a way that it has that shape. Easy question. Easy question. Will this graph ever cross the x-axis? No. Will it ever touch the x-axis? And that's why I like the asymptote. Because if you look at it, you could assume it might, right? You just look at it, you're like, oh yeah, it's going to keep going down, right? But we're going to put an asymptote in, because that asymptote is my borderline, right? So I'm going to say, okay, I'm going to draw in my asymptote. Here's my invisible borderline. And I'm going to write it as y equals 0. The asymptote is important. Because like Raleigh said, it does not touch, right? Okay, so domain. X equals all real numbers. Every possible x value can be on this graph. You don't see them all, but every possible x value can be on this graph. Range, we know it never touches 0, so it's y is greater than 0. What do you think? Thumbs up? Okay. Turn the page in a moment. Boy, that is really a nice overhead. That is bright. Okay, you ready to turn the page? Okay, now, what do you notice about example 2? It's going to be decay. All right, nice job. So it's going to be decay because you're going to take half of it and half of it and half of it. Okay. So again, if we did a t-table, okay, I'm going to go ahead and make a little t-table here. X and y, and I'm going to use values of 0, 1, 2, 3, 4, and then I'll go negative 1 and negative 2. All right. So if I plug in 0, anything 0 power is 1, and 1 times 48 is 48, okay? And again, if you need help, just use a calculator to get these values. You can. If I plug in 1, anything 1/2 to the 1 power is 1/2 times 48 is 24. 2, 1/2 squared is 1/4. 1/4 of 48 is 12. Do you see a pattern? What do you guys see?
Yeah, 6.
6, right? 3, right? Now, what do you think happens with -1? Let's check it out. It would go up. Yeah, it would go up. You're right. Let's check it out. Let's see if the oh, I really like that. Remember all the times I had to put the calculator in weird ways? Oh man, that is beautiful. So if I went 48 to the 1/2 to the -1 power, it does go up. 192.
That's -2.
That's
That was
negative two.
-2.
Thank you. To the 1/2 to the -1. 24. Yeah, thanks. Boy, I'm making all sorts of mistakes, huh? All sorts to the -1. How's that? 96. Thanks. Okay, now here's why that works. Let's take the -2. If I go 48 and I go 1/2 to the -2 power, watch. We know negative exponents, don't we? Flip it. Remember how I flip it because it's negative? Remember how we did that? So I got a 48. If I flip it times 2 over 1, you get 96, right? Okay, now I'm going to have to graph this. I might go by 5s. That would at least get me 48. If I go 10, 20, 30, 40, 50, 60. And if I graph it, I have my initial is at 48, which is about there. 24 for 1 is about there. 12 for 2. 3 is at 6. 4 is at 3. And then -1 is at 96, which is way up here, okay? Again, if I draw in this graph, it's going to have the same shape, that J kind of shape. And what do I absolutely need? What do I need? What do I need? Because does this line just flatten out here? Does it touch this? Does it go beyond this?
Asymptote.
You've got to have the asymptote. You guys agree?
Yes.
Because if you don't have the asymptote, we could say, oh, Mr. Davis, I think that graph's just going to go like that. No. Or, Mr. Davis, I think that graph's going to dive down in here. No. Oh, Mr. Davis, I think that graph's going to touch there. No. Put the asymptote in, because with the asymptote, it's a boundary line at y equals 0. There's my asymptote. Okay, now, domain and range, same thing, isn't it? It's just backwards. The domain's still the same thing, x equals all real numbers. It's forever wide, even though up here, it's still always moving over. You just can't see it. It's too high up, right? Range never touches 0, correct? So it's y is greater than or not equal to 0. Domain and range, okay? Now, Raleigh, I think we're going to answer your question on example 3. We are. We're going to get that R. We're going to get what R means in this equation, okay? So, a biologist starts with 100 bacteria. They're going to grow. They're going to grow exponentially, right? At a rate of 8%. So I'm going to use this equation. I'm going to give you the percentage one. I'm going to write y equals a 1 plus r to the t power. And I like t in this case because we're talking about time, okay?
And R equals 8%.
Yes, totally right. So this isn't that hard, is it? So y equals how many? What's my initial amount? What's a equal?
100.
Good. So we're going to put 100 here. 1 plus 8%, right? Which is 0.08, right? Because you got to move it 2 places. Got to move it 1, 2 to the t power. So here's my equation. If you want to rewrite it, you don't have to, but you could rewrite like 1.08 to the t power. You okay with that?
Oh, I remember this one.
Sure. So now, how many bacteria are present in one day? Well, this is all about hours, isn't this per hour? This is all about per hour, so easy question. How many hours?
24.
24. So let's let t equal 24, right? So I'm going to go y is equal to 100, 1.08 to the 24th power. And I have to use a calculator, right? Have to. So I'm going to go, all right, clear. I'm going to go 100 times 1.08 to the 24th power. And I get an answer about 634. And that's bacteria. Okay, and I didn't use any decimals because we're talking about number of bacteria, so I rounded it off to the nearest whole. All right, so what do you think? Pretty easy?
No.
No? Okay, so I'd like us to do the homework, and I'm going to help you out a little bit with the homework to start off with.